Hello everyone and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to talk about making file system images. So again, an overview of our high-level process. We started out with a call. Someone called us. We said yes, there was an incident. We did some live analysis and we decided to do some dead analysis, and now it's time to acquire an image or images and then proceed to do some dead analysis. And this is where the majority of forensic tools out there live, in this block here. If you're going to take an image, the first thing you have to decide is what format will that image be. There are a couple of different choices for image file formats. The easiest one is RAW. RAW is just nothing but all of the bytes from the file system compacted together in one big block. So a RAW image will be exactly the same size as the media. So some tools can operate on compressed images and some of them will not operate on a compressed image. Even if your tool will operate on a compressed image, it's going to be a lot slower because it has to uncompress the image all the time. There are also several proprietary formats, some of which embed the metadata into the file. So there's one big happy file, and essentially what they have is chunks of raw data with metadata shoved in every so often. That's another popular file format. You also have proprietary formats with the metadata in a separate file. So essentially what you have is a raw file and then metadata in a separate file. You can also create a raw image and then create hashes to store in a separate file. Now, a little bit about hashes. You should always be hashing these images. Now, we always will make an overall hash of the image. It's good to hash the subchunks of your image as well. Why would you want to do that? Well, there are a couple of reasons. If you have media that is potentially damaged, if one bit gets flipped on that entire 3 terabyte drive, the hash will come up different. You do not want to have to throw away an entire image file because of a bit flip. That's one reason. The other reason is if you recalculate the hashes as you go to verify that you haven't changed an image, it's helpful not to have to do that on the entire image. So we'll show you some tools that will do this for you. Now, there are different ideas on what format is best. There are people that like EnCase, which is a commercial tool for doing forensics. And they will tell you that expert witness format is the best format that you can use. I would disagree with that. I think that the raw format with a separate file full of your hashes is probably the best because every tool in the world will read a raw format file. Now, some of the proprietary tools will make that difficult for you, but it's still possible. So I like compatibility. So I like the raw format. So how do you create a raw format image? It's very simple to do. There is an ancient Unix utility called dd, which really just moves bits around. And on your Linux system, if you say dd and then you give it if equals and the name of your subject device, let's say it's /dev/sdb, and of equals the name of your image file, which might be your case number .img or this drive identifier, etc. And you can give it a block size. Normally, block size of 512 is good. You can improve performance by giving it a larger block size, but if you give it a larger block size than 512, you might have issues at the very last chunk because you need to use a block size that's evenly divisible into the size of your media. 512 bytes is the standard by far for sector sizes. There are a few file systems out there and a few drives out there that might have larger blocks than 512 bytes, but they're all multiples of 512. So this is the safest option. Some years back, a few folks got together and they wrote an enhanced version of DD just for forensic stuff. That product is called dcfl-DD, which should already be installed on your system if you ran the script that I presented in an earlier video. And it adds to the standard DD hashing. So you can tell it hash equals, and then you can pick an algorithm. Now the default is MD5, which I don't personally recommend. I recommend something like SHA-256. It's fast enough, and it's better than MD5. Then you can also set a hash window. Maybe you want to hash every megabyte or every 10 megabytes. It's up to you. Don't set this ridiculously low or you're going to have a huge hash file and it will take forever to make your image. You can also set a hash log and set that value equal to the name of the file that you want to create. If you don't set a file, it will send all of this information to standard error instead, and you need to capture it into a file. So if you're going to do this, you should probably be write blocking. Now there are commercial hardware write blockers available out there. Typically they work with only one kind of drive, although SATA is pretty much the standard today. They are out there for $350 or more, so they're not cheap. You can also use the USB write blocker as described in the USB forensics class here at Pen Tester Academy. The nice thing about these, they're cheap. They cost you about $25, but they're very slow. The microcontroller that I used to develop those is limited to full speed or 12 megabits per second only. And it's great for thumb drives, but if you have a 3 terabyte hard drive, you probably want something else. What could that something else be? Well, on the software write blocking side, you have a couple of different choices. You could use UDEV rules, also as described in the USB forensics course, or you could boot a live forensics Linux on the subject computer, something like SIFT or similar. Or you could boot the live forensics Linux on your forensics workstation and then mount the drive. I don't really recommend this method, and I don't really recommend booting the live forensics on the subject computer either, unless there's no good way around it. Sometimes you might have something like a laptop where the hard drive is not easily accessible. So you might decide that this is a better option. But in most cases, I think you're best off to pull the drive and image it directly. And we will talk about that in a future video. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, welcome to Linux Forensics here at Pen Tester Academy. In this video, I'm going to show you how you can make a disk image of your virtual machine hard drive Normally, you actually, if you just wanted nothing but a raw disk image, you can create one using the VirtualBox tools. However, what you can't do with the VirtualBox tools is hash every megabyte or so, as you can easily do with dcfl.dd. Before we get started, one thing I need to mention, there is the possibility to image a partition or to image the entire drive. Now, normally, I would recommend that you image the entire drive. You can choose to image just one partition. However, you might lose some information. Perhaps someone has stored information on a deleted partition, on unallocated space, etc. So it's always best to capture the entire disk if you can. If I go to my VirtualBox directory, so here I've gone to the appropriate directory where my VirtualBox files are stored. I do an ls-l. Now in this case, I've used a vmdk file, and part of the reason that I've done this is ActiveAt Disk Editor, which we'll talk about later in this course, will read this format directly. It will also read VHD files, but unfortunately will not read VDI files that are the native files for VirtualBox. But that's okay because VirtualBox reads all the other formats. So here you see this large 19 gigabyte flat file. This is my target. This is what I'm going to create an image of. Before I create the image, I'm going to run fdisk on this file, which some of you might not realize you can do. So I'm going to run fdisk on Pentester Academy subject 1 flat vmdk. And if I do a p command to print the various partitions, you see that I in fact have 3. I have the one Linux partition that's 16 gigabytes. I have an extended partition, and within my extended partition, I have a Linux swap partition. So notice it's partition 1, partition 2, and then partition 5 because this is inside of an extended partition. It's pretty typical. So I can go ahead and I can quit. Now, if I wanted to get just one partition, what I would have to do is alter my command to dcfl.dd to tell it to start at something other than the beginning and to end in the appropriate place. But we're not going to worry about that for now. For now, we're just going to get an image of the whole thing. So I can quit. And remember, my format was dcfl.dd, and I give it an input file or file system. In this case, it's going to be from my local directory, my flat file, and my out file, I will send it to an external drive that I've connected. There are a couple reasons that I'm going to do this. One reason is that I have an external USB 3 drive, and it's going to be a lot faster to write to that than to read from and write to the internal drive. So I'm going to create an output file. And my output file I will just call 2015.3.9 img. And I will tell it to use other than an MD5 hash. So I'll say hash equals SHA-256, hash window equals 1M, 1 megabyte, and hash log I will also set equal to media, fill, Toshiba, disk images, and I'll just call this one 215.3.9 hashes. Like so. And my command is off and going. Now this will take a little bit of time for this to run. I do have about 20 gigabytes worth of data. So I'm going to go ahead and pause the video, and when I come back, this should be finished. And so now it's done. So we've managed to write out our file. And if I change to that directory, do an ls, you can see that yes, in fact, I now have a 19 gigabyte file, and I also have a file full of hashes. So if I just look at some of the hashes, you'll see how this goes. It just has a range of values, and I set every megabyte, and then it gives me a hash. So you can see that this file system is actually a little bit empty because all of these values are hashing to the same thing. And actually, if you looked at the head of the file, you would likely see something similar. Not at the very beginning, but pretty soon you see this hash value repeated a few times. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. Help us spread the word. We'll see you next time. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, I wanted to talk about software-based write blocking. Namely, I wanted to talk about something called the ForDeck, which is an add-on to my Linux that runs on the Beagle family of devices known as the DEC, and it is intended to allow you to set up a magic hub so that everything that's connected to that hub is automatically mounted and automatically mounted as read-only. In order to accomplish this, I use some simple UDEV rules. If you're not familiar with UDEV rules, they handle how devices are mounted, unmounted, etc. on a Linux system. So what I have here is a basic shell script that will install the ForDeck. Now, I just recently came out with a new version of this, and the reason for that is that USB 3 hubs actually present themselves as two devices. One of them is a USB 3 hub, and the other one is a USB 2 hub. In order to handle those devices, which is something that wasn't supported by the BeagleBone, it does not do USB 3 at this time, I had to add the ability to add a second product ID to this script. Here's how it works. I have three possible parameters. You run the install script, you give it a vendor ID, and you give it at least one product ID, and optionally you give it a second product ID if you have a USB 3 hub. And how this works, it creates some UDEV rules, and UDEV rules are actually pretty simple. You can get more details on this, by the way, if you look at the USB Forensics course here at Pentester Academy. But in a nutshell, what this does is it says whenever I add a block device and it's downstream from this particular vid and this particular PID, set an environment variable, fill mount, set another one, fill dev, to the name of the device, add a script to the scripts that are to be run, and the first script is called protmount sh, and it is passed two variables, the name of the device and its number. So if it's SDB3, this first parameter is SDB3 and the second one is just 3. This script, which we'll look at in a second, actually generates another script that is run. The reason for multiple scripts, when these scripts are actually ran, they do not have all the information available. So when I originally insert a drive, it is not yet ready to be mounted. So I have to add some things to be run later. And when it's removed, I do the same thing. If it's a block device, it's being removed and it's downstream from the appropriate hub. Then I run a different script, prot3.sh, and I give it those same two parameters. Other rules say if it's a fill mount, if it's one of these special deals, then set the environment variable udisk presentation to hide. In other words, don't pop up a message, and set the hint to never, which means don't ever try to mount this, and call this script. And this script, again, was created by protmount. Similarly, when you unmount, it will run protmount 4 dash the partition number. So pretty simple. And then I have a second clause in this function, and its purpose is just to set up the second PID if there is one. So the first you test to see if there is one, and if there is, you do the exact same thing and add rules for that PID as well. And then these scripts get copied to etc udev scripts, and one rule is created in etc udev rules.d. And the name of that rule is right here. It's 10-protected mount rules. So how do you use this? It's very simple. I'll go out here to my terminal. So I've gone to my terminal. I need to run this as root. But before I do that, I'm going to grab my USB 3 hub. I'm going to go ahead and plug it in so I can get the appropriate vendor ID and product ID. If I do an ls USB, I will see that in fact, here's my USB 3 hub right here. And here is my USB 2 hub. So let's go ahead and install it. So sudo install --vid 05e3 --pid 0612 and --pid 2 0610. So if I plug in a drive, it should be automatically mounted and mounted as read-only. And I see it showing up here. And once again, I can type mount. And I can verify that yes, in fact, my device was mounted right here. I can see that it was mounted. And I see that it was mounted as read-only. That was a USB 2 device. I'll unplug it, check my mount. Notice it was successfully unmounted, and now if I plug in a USB 3 drive, it was also successfully mounted. And in this case, notice that I had 3 partitions. And all of them were mounted as read-only. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk about the process of actually mounting a physical hard drive that you've collected from your subject computer. So in a previous video, we talked about how can you collect an image from a virtual hard disk, but in the real world, you probably have some actual hardware in your hand and you need to image it. So that's what we're going to talk about in this video. Now, as a reminder, you should have some sort of write blocker installed, or at a minimum, at least set every device to not be auto-mounted when it's detected. That way, it's not mounted and mounted as writable every time it's connected to your system. That should be the minimum, and we talked about how you could do that in some other videos. So here I have some pretty simple devices. I have my docking bay right here. And this is pretty cheap. This is about a $35 item that you can get online. It's USB 3 and it supports 2.5 and 3.5 inch SATA drives, which are the most common ones that you'll encounter. And I also have here a nice inexpensive USB 3 hub. So what I'm going to do is just connect this, and I've set up this hub as my magic hub so that devices connected to it get mounted as read-only. So I'll go ahead and plug this in here. And I'll plug it into my laptop. So now it's been plugged into my laptop. I will power up the appropriate ports. I will also power up my drive. And this should allow me to read the drive on the computer. So if I do an ls USB, I will see here's my backup drive. It's on bus 2. And here I see my hub. I should also see another drive, and I believe it's this one right here. More importantly, if I do an ls on /dev sd star, now I see that I have my internal drive A drive B, and a drive C. So drive B is the Toshiba backup. I can verify this by typing mount. And when I do, I see that yes, in fact, this Toshiba backup drive is mounted and it is SDB1. Now I can go ahead and I can use DCFLDD. And as before, we talked about the fact that you can either do one partition or do the entire drive. I normally recommend you do the entire drive. So I will just go ahead to make my life easier. I'm going to change to this drive. And you see there's a previous image that we made from our virtual machine, 19 gigabytes. And I'm going to go ahead and make an image of this drive, which actually comes from my daughter's Linux box. So now we're ready to actually make the copy. So the command we want to use is dcfldd, and our input file in this case is /dev/sdc. That's the entire device. If I wanted just a partition, I could append a number to that. My output is going to be K Linux laptop IMG, block size of 512. We will hash with SHA-256, and we will set a window of every megabyte. And our hash log will be K Linux laptop hashes. And it will take quite a while for this to run. So now we have our drive merrily copying away. You can see that the light is flashing. And if I look over here at my external backup drive that's storing this image, you'll notice that this little blue LED is also flickering as the data is copied from one device to the next. So it's really that simple. It's in some ways a lot easier if you're using a physical device rather than a virtual hard drive device. But either way, it's not terribly difficult. Again, I definitely recommend at a minimum you disable automatic mounting. There is absolutely no reason to mount this drive onto your computer right now. You can simply have it set so that nothing gets mounted, or you can have it automatically mounted as read-only, which is not actually what you want in this case. So that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you next time. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, I wanted to go over some basic information concerning master boot records. In particular, we're going over this now because we're about to mount some images that we created previously. So once again, just an overview of our process. We got a call. Someone said, I think there's been an incident. We said, yes, there has. And we decided to do dead analysis. We've acquired the images, and we're now getting ready to get started with analyzing those images. So the first thing we want to do is mount them. And this makes our life a lot simpler. I mean, we could just examine the files directly and never mount them, but why would you do that? That just seems really hard to me. So if you can mount them and mount them as read-only, you can more easily investigate them. Master boot record is an ancient standard. This came from the 80s. I want to say it's even the early 80s. So it's been around for something like 30 years. And it allows you to have up to 4 partitions. I'm sure at the time that this was first created, they thought, who would ever have more than 4 partitions? You know, who would ever need more than 640 kilobytes of RAM? At most, one of these 4 partitions can be marked as active. That means bootable. It makes sense, right? You couldn't have more than one marked as the boot partition. You certainly could have an entire media with no bootable partitions. Now, if you want to have more than 4 partitions, which people do nowadays, you can use what we call an extended partitions. And we'll talk more in detail about extended partitions in a future video. Extended partition is something that has multiple partitions inside of it, and it stores these partitions in a linked list format. Also, something you should know, this whole MBR thing is old and it's being replaced. It is slowly being replaced with GUID partition tables. So GUID stands for Globally Unique ID. So you might notice that your Linux system has a very long volume name for all your partitions. That's the globally unique ID for that partition. It's set up so that you can have these unique IDs for all of your partitions, and you can store lots and lots of partitions on your disk. And we'll talk more about that in a future video as well. For today, we want to keep it simple and talk about the good old MBR. So what does it look like? A master boot record looks kind of like this. Starts out with 446 bytes of boot code, and then it has its 4 entries. It ends with a signature. The signature it ends with is the bytes 55AA. And that says, I am the end of an MBR. It's also a signature for something called a boot sector that we'll talk about much later in this course. So what is this format? Well, it starts out with 1 byte that contains an active flag. So if this first byte is hex 80, that means this is the boot partition. If it's 00, it means it's not. It then has the start head, the start sector, which is stored in the lower 6 bits of this byte, and the upper 2 bits of this byte are the upper 2 bits for the cylinder, which is stored in the next byte. So the way this works, you have 1 byte, which can store up to 255, and then we add 2 bits. So we have a 10-bit number, so that means a cylinder number in this system can be as high as 1023. So that is how this is done. Now, typically, we don't really worry about this with our Linux systems. Following this information, in the 4th byte, we have a partition code. Now, type 83 hex is the most common that you'll see. That's Linux partition. You might also see things like 82 for Linux swap, or 85 for Linux extended partition, etc. And we'll talk more about those later. Then we have the same information in the same format for the end of the partition, the end head, end sector, and cylinders. What we're more concerned about, it has the sectors preceding the partition, and this is stored in little endian format, and also the total sectors in the partition. So how can I mount an image with an MBR? Well, let's show you how we can do that very easily here on the command line. So here I am on the command line. Now, the Linux fdisk tool can be used on an image file, not just on an actual device. So I will go ahead and I'm going to run this. So I'm going to run fdisk. And before I do that, I'm going to be a little lazy. I'm going to run media, fill. I just want to get my path to an image. Now, this is not the image that we've been looking at, but I just wanted to show you this because this does not have any extended partitions in it. So if I run fdisk on this image file, and I type P for partition type, I will see that this is a type B, which is Windows 95 FAT32, And here's the important bit of information. I really don't even care what this is because Linux is smart enough to mount it for me. I normally don't have to specify any kind of a type. This is the only thing I care about. It starts 63 sectors into this image. So I'm going to go ahead and type Q to quit, and I will make sure I have a place to store this. So I'm going to go ahead and put it, I have a media part 0 directory that I've already set up. So I will just type mount. And once again, I'm going to mount -O for options. I'm going to mount this as read only. Give it the option loop and the option offset equals. And now I have to give it the offset in bytes, not in sectors. So if I'm lazy, I can always pull up my calculator and I can type 63 times 512 bytes per sector, and I see my offset is here. I can copy and then I can paste that in here. I also want to give it the no access time updating. Then I will give it my source of media, Phil, Toshiba, disk images, DF 217DD, and I will mount this to media part 0. Boom, done. So if I do an ls on media part 0, sure enough, I have my file system mounted. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, I wanted to show you how you could use a simple Python script in order to mount an image from a system that is MBR based, master boot record based, without extended partitions. So what I've done is I've created a pretty simple Python script. I import a couple of required items, namely sys, which allows me to get command line arguments, OS path, which allows me to test for files and directory to see if they exist, and subprocess, which allows me to create a new process, essentially to run shell commands from within my Python. Now for now, I'm going to skip over this class definition and we'll start down here. So here I have a basic usage function. What does it do? It just types out, hey, here's how you use this script. You call it and you give it an image file, and it will attempt to mount partitions from that image file. Here's my main method. Did you give me less than 2 arguments? That means you gave me nothing, because there's always one argument that is the program that you ran. So if you did that, I call usage, which will exit my script. If not, I will check and see if the file that you specified on the command line exists, and it's really a file. So that's sysargv1. Sysargv0, again, is the program that you're running. If it doesn't exist, I will complain to you, and I will say, print out this message, file sysargv1 can't be opened, and I exit. By the way, of course, you're going to run this script as root because you can't mount anything if you're not root. I didn't put a check in here to see if you're root. I suppose I could have. Here, I opened the file, and this is a somewhat recent construct from Python, and it's preferred to other methods where you might open and check for an error, or you might put stuff in a try-catch block. If this looks new to you, it's because this is somewhat new to Python. I want to say Python version 2.5 and newer have this ability. and it's called with open. So I open my file as read-only in binary mode, which, by the way, in Linux is not really required, but this is good for compatibility with Windows. So what I'm doing is I'm opening my file, and I'm going to call that file object F, and I'm going to get the first sector. So the first sector I'm going to convert to a string, and I'm going to call read on F, and I'm going to say, please give me 512 bytes. Then I check, and I say that sector, are the last 2 bytes 55 AA? If they are, that tells me this is either a master boot record or something called a volume boot record, which is a Windows FAT file system thing. We won't talk too much about FAT file systems in this course. We might in a future course, say on Windows Forensics. If this is an MBR, then these bytes for the 4 partition entries should either be 80 or 00. So I do a little check, and I say, are all of these either 80 or 00? If they are, then it must be an MBR. Now, if you look down here a little bit, you'll see else, it must be a VBR. And I will go ahead and try to mount it. So this script isn't necessarily specific to just Linux partitions. So back to this section. I create a list, and I call MBR record, which is the class I defined earlier, so we'll get back to that in a bit. And I pass it my sector, and I give it an index. And this will generate up to 4 partition entries called parts. So now I have a for loop, and I say for P in parts, print it out, print out the information, and if this partition is not empty, then I will try to mount it, assuming the partition type is not 238 or 5. And I should probably update this with some additional partition types as well, because there are other extended partition types. By the way, 238 is a partition type for something called a globally unique identifier partition table. And if it's one of these, I say, sorry, I don't support that in the script. Otherwise, I try to mount it. So I say, what's my mount path going to be? Where am I going to put it? Well, I'm going to put it under media part %s, and I'm going to substitute for %s the part number as a string. And if that directory does not exist, I will create it. I will call subprocess call make directory for that mount path. My options for mounting will be loop. It's a file, not an actual device. Read only. Please don't update the access times. I will set my offset equal to something I'm going to calculate, and I'm going to calculate it as the start. And again, recall from the previous video that start means the starting sector, and the sectors are normally 512 bytes long. That's my offset, and I call mount. And that's it. And here I have a little trick that some of you might be familiar with. I say if _name _equals, and then in quotes _main _, then please run main. All right, so let's go back to our class. So here's my class. Every Python class should have a constructor defined, and here I do. I've defined my constructor, which is called _init, _, and every class method in Python starts with a parameter of self. Parameters that are passed in are sector, which is my 512 bytes for the sector, and partition number, starting with 0. I then set the partition number equal to what was passed in, and I calculate my offset into the 512 bytes as 446 plus the partition number times 16. Recall there are 16 bytes per entry. I say this is not active, and then I check, and I say is the very first byte 80, then I set active to true. Now I will look at the type, and I will say the type is equal to the ordinal value. This is an easy way of saying what is the value stored in this byte. And it's stored in the 4th byte, actually the 5th byte, but it's offset 4. That is partition type. And I say it's not empty. But if the type was 0, that means that it is in fact empty. If it's not empty, or even if it is, it doesn't hurt to make this calculation. I say what is the starting sector? How many sectors before it? And it's stored in little endian format, so it's just the first byte plus 256 times the next byte plus 256 times 256, also known as 65,536, times the next byte, and then 256 times that, or this value, 16,777,216 times the last byte. The same thing is true for the total sectors. So it's the exact same calculation. I define this method called printPart, and it has only one parameter, self. And if it's empty, I just print empty. Otherwise, I print out, if it's active, I print out bootable. And either way, I print out the type, the start, and the total sectors. We'll go ahead and run this script real quick. So I'm going to type mount image pi, and I'm going to pass it media, fill, Toshiba, disk images, df2, 17dd. And there you have it. It says it looks like an MBR. It has one bootable partition, which is type 11, which is a FAT32 partition, starting at sector 63, and this is how many total sectors it had. The other 3 entries were empty, and if I do a quick mount command, I should see here at the bottom, in fact, I have mounted this file on media part 0, and it's a VFAT. So if I do an ls on media part 0, there it is. Exactly the same as in the previous video. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about mounting images that might contain extended partitions. Again, here's our high-level process. We're getting into the dead analysis, so we've acquired images, and now it's time to actually mount them. Extended partitions. When are these used? Whenever you have more than 4 partitions on an MBR-based drive, you have to use these. Now, you can actually use these if you have less than 4. It's not terribly common, but you can do this. And a primary extended partition stores this logical partition inside of itself. Each extended partition, we normally call the overall partition a primary extended partition, and it will store inside of itself multiple logical partitions. And each logical partition is preceded by an MBR sector. So it has the exact same format as the MBR we talked about in a previous video. A couple of differences, however. First of all the offsets are relative to the extended partition, not the overall media. Also, this is interpreted as a linked list. So the first entry will point to your first logical partition. If there is more than one partition in the extended partition, the next entry will point to another extended partition. That's why it's interpreted as a linked list. Now, normally the last two entries are not used. You could put something in there, but there is no operating system out there with a tool that will let you do this. I won't guarantee what's going to happen if you try to manually create one and then see what each operating system does in order to interpret it. Some of them might just ignore it, and some of them might interpret it and do something strange. So what does this extended partition look like? This MBR, if you will? Well, it looks exactly like a regular MBR. It starts with some boot code. In this case, it's not really used for anything. And then you have your first partition, and then a second partition, if any, followed by a bunch of zeros and your signature 55AA at the end. And each partition record looks the same as what we had before. So how do we mount these extended partitions? Well, it's pretty simple, and actually it's the same process. So how do I go about this? I need to run fdisk on my image. So if I run fdisk on my image, which I have stored to an external drive, so I run fdisk on that. And if I type P, it should print out my different partitions. And notice that I have a Linux partition, type 83, followed by an extended partition, type 5, followed by a swap partition. And notice that the swap partition is, in fact, stored inside of this extended partition. So if I wanted to mount this as a partition, in this case it's not a regular partition, but if I wanted to try and mount this as a partition, all I need to do is exactly what I did in the previous case. I just need to get out my calculator, and if I run my handy dandy calculator, I take this value, this starting value of 33556,480 times 512, and I get that value and I copy it, and then in my mount command I give the option offset equals this value, and then it will mount my partition. And it's that simple. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone. Welcome to Linux Forensics here at Pen Tester Academy. In this video, I want to talk about how you can use Python in order to automatically mount, read-only of course, some extended partitions which might have been found inside of your disk image. What I have here is a pretty simple Python script, and of course it starts out with shebang, user bin Python. I import the same modules, sys, os path, and subprocess. And I have the same MBR record class that we used before. And recall that we said that the MBR record format was used inside of our linked list. Recall that we said the MBR format was used for the linked lists inside of our extended partitions. So that's completely the same. We have a usage function. It is the same format. It takes one parameter, the image file. And here in my main method, I've defined two lists. I have a list of extended partition types and a list of swap partition types, because you normally don't want to try to mount a swap partition. So we need to detect that and just skip over it if we have an extended partition that happens to be a swap space. So as before, I read in that first sector, that MBR, and I iterate over it looking for extended partitions. Now, in the other script, we had some logic that said if it's just a VBR, go ahead and mount it, but that's not what the script is for. So this script is just for mounting things in an extended partition. And it's something that you could run after the first script if you detected that you had some of these. So I read in my two values. If in fact it's an extended partition, that's what this test does. It says if the type for the current partition out of my 4 primaries is in fact an extended partition, it prints out a little message telling me that it found it, and it sets a variable called bottom of rabbit hole to false. And it says this extended partition starts here, and I will start with partition number 5 for extended partitions. And then I have a while loop that says, while I've not found the bottom of the rabbit hole, get those linked list entries. Recall that we said the first 2 entries are used for extended partition tables. So I have the same open. The only thing that's been added, now I have a seek command. So I say, let's seek to the appropriate sector, and here I have to use bytes, so I multiply by 512. And now I read in that sector, which is an MBR, but it has my linked list entries. I create a small list with 2 items. The first entry, which points to my file system, and the next entry, which might point to another extended partition, or nothing. If it points to nothing, then I'm done. So I'm going to look and make sure that this first guy is not a swap partition. If he is, I'll just print a message saying I'm going to skip him. Otherwise, I'm going to try to mount him just as I did before. So I'll say, if the directory doesn't exist, create it. Here are my mount options. And the biggest thing I need to do is calculate this offset, which will be the start of my extended partition plus however far I have to go into it here, because recall again that the extended partition, all of the values in the MBRs for the extended partition are in fact relative to the start of that extended volume. So I will print out a message saying I'm attempting to mount something, and then I will call mount. If the second entry has a type of 0, then I'm done. If not, I'm going to add the start of that partition, which is another extended volume, to extend part start. This is the sector in the entire disk where that partition starts. And I will also increment the partition number. So now if you look, what's going to happen? So that's the bottom of my while loop, and it says Oh, I'm not at the bottom of the rabbit hole. If I got back here, I'm going to open. I'm going to seek to that new starting point. And then I'm going to pull in the 2 MBR records, etc., until I reach the bottom of the rabbit hole. And that's pretty much this script. I can go ahead and I can run my script. And I'll run it on mount image expart pi against media fill Toshiba disk images and this image right here. And sure enough, it tells me, hey, this looks like it's an MBR at the start. It had one partition that was a type 83 Linux. And then there was another partition, type 5, which is in fact an extended partition. And it tells me, hey, I found an extended partition right here. And then I found a swap partition, so I skipped over it. And in fact, I found the bottom of the rabbit hole. Then I looked at my 2 other entries, and they were both blank. So there you have it. Well, that's all for this video. As always, if you're enjoying these videos, please tell a friend and help us spread the word about Pen Tester Academy. See you soon. Hello everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about GUID partitions. As we said in some previous videos, the GUID partitions are kind of the new standard. And as a reminder, we're just getting started here with our dead analysis. We have acquired our images, and now we're getting ready to analyze them. So more about GUID partitions. Now, these are part of the UEFI system that's replacing the BIOS booting process. So you're probably familiar with the BIOS and having to make settings and change some settings in your BIOS. And there are some disadvantages to the BIOS. The BIOS is going to try to boot your computer in 16 and 32-bit mode, and you have this nice modern hardware, and it just can't take advantage of it, at least not while it's booting. So the whole idea of UEFI is that it's supposed to replace this. Now, when it comes to GUID partitions, it allows up to 128 partitions. So that's great. There's no more worrying about, I have 4, I need more than 4, I have to have an extended partition, and I have to do all this craziness. It's very simple. And as I said, it is the new standard. So all current 64-bit systems ship with this. You know, if you buy a new computer that's a 64-bit computer, which most of the computers you would buy today are, it will come with a GUID partition system installed. So what does it look like? Well, we start out with our good old friend, the MBR. And here there's a reason for this. We have this protective MBR at the start because we don't really know what's going to try to read this. You might have an old system that tries to read this drive, and you don't want it to overwrite your drive. So it will say this entire drive is one big partition, then it's normally a type EE, which your old computer will say, I don't know what that is, and it'll ignore it. The next block will have your primary GPT header, and then you will have your various entries. So if you have a 512 byte sector, you will have 4 entries per sector because each entry is 128 bytes. So this is repeated until we get to LBA 34, and that is where the actual partitions start. Now, another interesting thing is notice that we have a secondary GPT header in the very last block, and then we have a repeat of our partition table entries. So this gives us a nice backup. If you're familiar with some of the Windows file systems, such as FAT32, you know that there's a backup boot sector. Unfortunately, it is only 6 sectors away from the primary one. So if there is a defect in that area of the disk, it might lead to trouble, even though you have a backup. So the idea here is that you have the entire disk separating the primary from the backup. That way, there's a lot less chance of both of these failing at the same time. So each partition record starts out with a partition type, GUID, and these are from a set of predefined types. And then you have a unique partition GUID, and then an 8-byte value for the first LBA, then an 8-byte value or 64-bit value for the last LBA, 8 bytes worth of attributes, and then a partition name that can be up to 72 bytes long. Now this is normally stored in Unicode, so this gives you up to 36 characters. What about the attributes? Well, the attributes are grouped together in chunks. So the first bit 0, says this is a system partition. So if that bit is set, that means that the operating system must preserve this partition as it is. It cannot change it. If the second bit is set, that says this is an EFI firmware partition. So don't change it, but just plain old ignore it. If the third bit is set, that is the same thing as having hex 80 as the first byte in your master boot record. That's the way of saying this is a bootable partition. We have a whole bunch of reserve space. They should be zeros. And then at the top part, we have in bits 48 through 63 a type-specific bunch of attributes, which varies by the type. Now, in the case of Windows NTFS partitions, bit 60 is used to indicate read-only, 62 as hidden, and 63 means please do not auto-mount it. So how do we mount these on our Linux system? Well, it turns out pretty easily. So let me just show you my computer, being a somewhat modern computer, naturally has GUID partitions. So if I do an fdisk on my A drive, SDA, and print out my partitions, you'll see that in fact I have 7 partitions. I have a Windows recovery partition, an EFI system partition, a Microsoft Reserve partition, and then I have 2 Microsoft Basic Data partitions. And in the middle, between those 2 partitions, I have my Linux file system and also a swap partition. So how do you mount this? This is super simple. Just like the MBR case without an extended partition, if I want to do this by hand, I have the start. I take the start and I multiply that number by 512, and I give that as an offset to my mount command, and it's done. It's that easy. In this case, I'm not going to mount these because they're not in an image file. As we've seen before, you can use fdisk on an image file just as easily as a physical device. And one last thing I wanted to show you in this video. I can use dd if equals dev sda. I won't give it an out file because I'm going to go to standard out. I'm going to give it a block size equal to 512. I'm going to give it a count of 1. And what this will do is it should print out one sector to standard out. I will pipe that to xxd. And sure enough, here is my first sector. And what's in there? This is my MBR. Notice I have a file type of EE. And it tells me, if I decode this, this is the entire partition. What about the next one? So I can give it the command to skip, and I'll say skip equals 1. So I will skip the first block, and now I will print the second block. Well, what's this? This is that GPT header, the primary one. If I skip another, so I say skip equals 2, this gives me my partition. So here's my first partition. And again, these are 128 bytes long. So it goes from here down to here. And you'll see what's the name? Basic data partition. Well, that's what we saw earlier. We can also see the attributes. The attributes are set. Recall from our presentation that bit 0, which when set has a value of 1, indicates a system partition. I look at my third partition. Here he is. Microsoft Reserve partition. And finally, in this sector, I have a basic data partition. This is continued into the next sector. So I can skip 3, and I should have 3 entries. Here's the first entry, the second entry, and the third entry. Now, of course, you could get all of this and put it into a file or redirect it to the screen, your choice. And you would just need to modify this command slightly. And instead of saying, I want to skip all of this, I can just say, I want to get the first 4. And that should give me everything that I want. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, I'm going to show you how you can use a fairly simple Python script in order to mount GUID partitions from an image file. We talked about ways of mounting other partitions automatically in previous videos, and so this is our last video on mounting images. So here's my script. I start out with shebang user bin python. I import a couple of Python modules, and this here is a list of GUIDs for partition types that are supported. In other words, things that we can mount. And you'll see that this list is pretty long because Linux will mount most anything. And I'm going to skip down here to my main for a second. And here, in my main method, I say, did you give me no arguments? Did you not give me an image file? If you did not, I'm going to call usage, which says, please give me an image next time. And then I check the first sector. I pull the first sector. Recall that the first sector will be an old school MBR. So I get the MBR and I check it and make sure it really is an MBR. And in most cases, it should be an MBR with one partition, and that partition type should be EE. So I check for that. And if that's not the case, then I'm going to tell you that it failed the sanity check. Then I'll do another sanity check. And I will look at the header for the GUID partition table. That is in the next sector. So I open the file, I seek 512 bytes, one sector, and then I check and make sure that it starts out with the string EFI part. And if I did find that, I print out a message. I then open the file, seek past those first two sectors, and then I pull in 32 sectors. So 32 sectors should have all 128 entries. I then define an empty list, and I iterate over that list. For each of these, I call GPT record. I create an object of that type, and I give it the entire thing with an index. And we'll look at that code here in a second. Then if it's not empty, I print out some information, and I append it to my list. So here, I say if the partition type is in my supported list, which we saw earlier, print out that it seems to be supported, and attempt to mount it. And this mount process is the same as what we've had before. And that is pretty much our script. So let's go back. This MBR record class we've seen before. It's unchanged. That's just for reading the first sector. Here, I take the entire list of 128, and then again with an offset. I set the partition number equal to what was passed in, and my offset is just the partition number times 128. Initially, I say it's not empty, and then I get the partition type. And I call this little helper method called print GUID. I give it the appropriate substring, which is offset to offset plus 16. Because recall, these are 16 bytes long. And then I check, and here's that helper method, by the way. It's a little bit of Python magic using things such as unpack and format, and then using this zero fill option in order to put any leading zeros in this string. By the way, one thing that's a little weird about these strings, they're little endin for the first 3 entries and big endin for the last 2 entries. So something to keep in mind if you work with these a lot. So here I say, is it empty? This is the empty partition type, all zeros. If so, then I set empty to true. And I set the partition GUID using that same helper method, first LBA, last LBA, using the unpack method. These are little end-in format 8-byte numbers. I'm doing something a little bit strange here. I have this name index, which is set equal to the location of 0000 if it's found. And the reason for that is sometimes you have Unicode strings that are null terminated, and then sometimes they have other weird terminators. So I've seen cases where you'll have a null terminator like this, and then you'll have some junk behind it. And I didn't want that to mess up our script. So in order to not mess up the script, if I don't find that null value, I will look at the entire string. Otherwise, I will look at the substring up until that null value. And this encode UTF-8 will convert from Unicode to ASCII. I have this other method that will print the partition, and that's pretty much it. So that is that script, and we're ready to move on and actually start analyzing our images because we now have found a way to mount all of them. So now we're going to try to run our script. Now, by way of warning, I don't have an entire image for my hard drive on my laptop that I'm doing this video on. So I'm just going to run this script, but not as root. So all the mount commands will fail, but they were going to fail anyway because there's actually no data there. So if I go ahead and run my script on my parcel image, I will see that it prints out several partitions. There should be 7 of them. The first one has scrolled just off my screen. Here it is. And then it will go through the list of partitions that I think are mountable, and it will try. So here it tried to mount these 3 partitions, and of course they failed because I'm not running this as root. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend, help us spread the word. We'll see you soon.